Okay, we're going to look at the fundamental counting principle. In the previous assignment, you looked at how do you find out how many are in the sample set. And you used some ways to do it. You used a tree diagram, and your tree diagram was really easy if there weren't a lot of things to work with. For example, if I'm flipping two coins, a tree diagram is easy because my coin can be heads or my coin can be tails, my first one. My second coin can be heads or tails. And the same thing here, my second coin can be heads or tails. So this gives me a sample set of heads, 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 tails, tails, heads, and tails, tails. So that's not hard to do with that many. But what happens if you keep adding more and more and more coins to the flipping? Instead of 2 coins, say you had 10 coins you were flipping. Now you have a lot more possibilities, and the number gets so big that it is really unwieldy to work with it with a tree diagram. If you're doing 2 dice, for example, 2 die, and you want to know what happens when you do those 2 die and they're 2 different colors, a red and a blue or something like that. 1, 2, 3, 4, 5, 6, 7. Okay? And the top is going to be what happens with the die. We can have each one of these numbers will be rolled by my die. And the same thing's true on the other side. And in this case, we can use a chart type of diagram to see what it would be, okay? So now, let's choose another color. And 1, 2, 3, 4, 5, and 6, okay? So now, if I'm going to actually have those 2 thrown, this one would be a 1, 1, okay? So we'd have a 1, 2, no, a 1, 1, sorry. Put the wrong one down, a 1, 1, a 1, 2, a 1, 3, a 1, 4, a 1, 5, and a 1, 6. Okay? Now let's look at the other one. We'd have a 2, and all of these would roll a 2. And so then we'd have the same possibilities here. And it would carry all the way across. So if we were to look at this as a way to get our sample set, we would find out that we have 36 possible in this sample set. Okay? Now, that's one way. This is a couple ways to figure out your sample sets. But if you've got a lot of things to do with it, neither one of these is going to be very usable because it gets so big that we can't do anything with it hardly on paper. It just takes so much and so much time. So what happens? There has to be another way to do it. And so we came up with the fundamental counting principle. And if you have many elements to deal with, this is a very good way to do it. So your fundamental counting principle, often referred to as FCP, your fundamental counting principle, is very useful. When there are repetitions of the same experiment, or a sequence of experiments. Okay, so what happens with your fundamental counting principle? It is a method to find the total number of outcomes with a sequence of experiments, a sequence of K1 experiment, in other words, your first experiment until the very last time you do that experiment. And that's what that K1 to Kn means, okay? So, how do we do this? Well, let's go back to our coins. The first time you flip a coin, you have two possibilities. The second time you flip a coin, you have two possibilities. The third time you flip a coin, you have two possibilities. The fourth time you flip a coin, you have two possibilities, right? So, how many total outcomes do we have? Well, 2 times 2 times 2 times 2 is going to equal 16. So if you're going to flip 4 coins, you're going to have a possibility of 16 different outcomes. Okay, now, if you think about your probability exercise page, the first page of that and the first column has all the possibilities for flipping 4 coins. And if you count that, you will find that there are 16 total outcomes. Okay, so let's just look at that. If we looked at that page of 16 total outcomes and we ask how often, what is the probability of rolling only one head? Okay, your probability of rolling only one head means that I have 16 possible because we found out from the counting principle. But how many ways can one head show? Well, it can be the first one, it can be the second one, it can be the third one, and it can be the fourth one. So there's 4 different ways one head is rolled. So therefore, our favorable is 4, meaning 1/4, which is equal to 0.25. So there's your probability, a 0.25 chance of rolling only one head when you do 4 coins. But we found out the total number in our set by doing our counting principle. So that's really important. So now let's look at another example of this. So here would be a series. How many different menus? Are possible from 15 appetizers, 12 entrees, and 8 desserts. Okay. I think that's spelled right. Okay. How many different menus are possible? Okay, this is a sequence of experiments. So, my first sequence is 15 appetizers times 12 entrees times 8 desserts is going to equal, when you multiply that out, you have 1,440 different meals. And this should probably be meals instead of menus. Okay? 1,440 different meals. A lot more than you probably thought ever could happen. So, as you can see, how do we work with our fundamental counting principle? It is through multiplication. In other words, my first experiment times my second experiment times my third experiment until I've done all my experiments. And so that's how you do your fundamental counting principle. It's through a multiplication of all the items. Okay, now let's look at how this is used in another way. Okay, a free throw shooter has a 70% success rate. Well, let's get 2 E's there. Free throw shooter is what's called a 75% success rate. That means he makes 3 out of 4 shots, right? Because that's 75%. So, what is the probability that, and this is equal to a 0.75 as a decimal because we need it as a decimal. What is the probability that he will make 5 in a row? Okay, so 5 in a row. He has a 75% chance of making the first one, a 0.75 chance of making the second one, the same thing for making the third one, and the fourth one, and the fifth one. So, we multiply all those together, and what do we find? It's a 0.2373. If you turned it into a percent, it would be a 23.73% chance of making those. Not very big, because the more you want them to make in a row, the lower and lower the probability is going to go. Okay, now let's look. How about missing 3 in a row? Well, first of all, we need to know what is the probability of missing. Well, if I have a 75% chance of making it, that means 100% minus 75% is equal to a 25%. So I have a 25% chance of missing 3 in a row. So let's look at that. 25% chance of missing 3 in a row, that's going to be a 0.25 or a 0.25. So 3 in a row, 0.25 times 0.25 times 0.25, and that's going to equal a 0.0156, which is going to be a 1.56%. Okay, not so bad there. We have a much greater chance of making 5 in a row than we do of missing 3 in a row if we're a 75% free throw shooter. Okay, so how else do we use this? There's a lot of different ways we use this fundamental counting principle. Here's another way. How many different 5-number zip codes can be made? And 0 cannot be in the first one. Okay, so first of all, how many digits do we have? That's where we have to start with this. How many digits do we have? Well, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So we have 9 possible digits. If we say that the digits cannot be repeated, okay, so our first one is going to be without repetition of digits. So our first slot cannot have a 0 in it, so that leaves me only 9 digits possible for the first one. Now we have 4 more slots to put our zip code, to build our zip code numbers. Well, one number has already been used for the first one and it wasn't 0, so now that leaves us 9 possibilities for the second one. Because we took the 0 out for the first one, but now one number's been used and it's not a 0, so 0's back in the possibilities, leaving 9 for the second one. But now what's there? 2 digits have been used, there's 10 total. So that means that the next one has 1 less than the one before, and therefore we end up with 9 times 9 times 8 times 7 times 6, which means that if we do not repeat digits, we have 27,216 possible 5-numbered zip codes. Well, we're getting to the point in the US that's long gone. We needed more numbers than that. So they decided to let digits be repeated. So if we do repetition with repetition, that means if I wanted, I could have a zip code of 99999. In other words, 5 nines. Again, 0 will not be permitted for the first number, the first digit. So I have 9 possible for the first one. And now, because all the numbers are possible and they can always be repeated, I have 10 possibilities for all the others. Therefore, 9 times 10 times 10 times 10 times 10 is going to equal 90,000 possible zip codes. So you see, this is a way to find out the possibilities in your sample set. And it's really, it makes the job easier. Okay? So let's go back to that bag of marbles that we talked about earlier. And I don't know if I'll choose the same numbers. I don't think I did. But let's pretend we have another bag of marbles. And in this bag, we have 6 red, 12 blue, and I put 15 white in this bag, making a total of 33 marbles. Okay? Now, let's look, how do we figure out what our probability is of drawing a red marble 3 times? Okay? We're going to do it first without replacement. Okay, so if I draw a red marble on the first one, I have 6 out of 33 chances of drawing that red marble on my first draw. Now my second draw is going to have 1 less red, so that leaves me 5 red, and 1 less marble in the bag, so that's 32 marbles. So my second draw has a chance of 5 out of 32. My third draw has a chance of 4 out of 31. Again, because every time you draw a marble, it reduces the number in the bag, and it reduces the number of red marbles. So this gives me a total of 5 over 1364, which is equal to 0.0037. Okay, usually these I go at least 4 places past the decimal, and that gives me a chance for 100th place if it needs to be turned into a percent. So I have a 0.0037 probability of drawing 3 red marbles in a row out of the bag of marbles. Now what would happen if I drew it and put it back in? So if I drew it, this would be called with replacement. So in this case, I'm going to draw 6 out of 33 because I put it back in. I have the same number of possibilities, put it back in, and again I have the same number of possibilities. And this is going to equal 216 over 35,937, which is equal to 0.006. So as you see, there is some difference there as to the probability of drawing these. And this is how you use your fundamental counting principle to be able to use it in probability. Okay, have fun with your assignment.